Hi everyone and welcome back to the series Build a Large Language Model from Scratch. In previous video, we implementing here the Multihead Attention wrapper class. Now in this video, we can implementing here the Multihead Attention with weight split. So far we have created here a Multihead Attention wrapper class to implement here the Multihead Attentions by stacking here a multiple number of single head attentions. Now let's see what is the importance of using here this weight split. Let's go on the book. So this is a book by Build a Large Language Model from scratch by Srivastava and Rashka. And then you can see here 3.6.2 implementing with multi-hat attentions with weight split. So in previous video, what we can do basically, we have one input of X, and then we have the two weight matrix of the WQ1 and weight matrix of WQ2. So, and then we perform here the two matrix multiplications to obtain here the two query matrix of Q1 and Q2, that you can see d out is equal to 2 and d out is equal to 2. I mean, we separately creating here the two weight matrix for that. But now in this one, we're simply going to creating here just one single weight matrix, which is a large weight matrix, and we multiply them with the input X. And the dimension is obviously the d out is equal to 4. And then after that, we obtaining here a query matrix with only one matrix multiplications. It's mean, see, if I have the more amount of the weight matrix, so matrix multiplication chain is quite large. So in these cases, the matrix multiplication, the multiplication is also reduces. That's why actually using here this weight split. And after that, we got here the queries that you can see Q, and the dimension is d out is equal to 4. And after that, we split the queries into the Q1 and Q2, which is nothing but my hat dimensions. So if I go on here, I also copy the image from here and passed it in my middle, so you can see the same images that you can see in our book. So it's basically it basically nothing but our the head dimensions. Okay, it's our head dimensions. So for each of the head dimensions, it's nothing but the d out. The formula is nothing but the d out divided by the number of heads. Okay, let's say divided by number of heads. I mean, how many heads you have, and then we divide them that. So in this scenario, our d out is nothing but the 4, and our number of heads is essentially 2. So we got here the 2 as our head dimensions. If I go on the previous code that you can see in our previous code, we essentially using here the number of head is equal to 2, that you can see, and the d in is 3 and d out is 2. But in the real case of the GPT, it's basically using the same size of the D in and the D outs. Now, what I can do is simply going to implementing these ones, and we explaining all of the steps, I mean, the line by line. I mean, how the vector is represented, because in those code we are basically using the 4-dimensional spaces. Okay, so now let's go on the code and try to implementing here the multi-hat attentions with the weight splits. So for that, what I can do, I am simply going to creating here a class called the multi-hat attentions. That's a class, the multi-hat attention. Okay, should be the attention, and then we are going to using here nn dot module. So this is the wrapper class. If you see my previous video about the multi-hat attentions, we just stacking all of the causal attention on here in the module, but in here you're not going to do that. Cool. So now what I can do is simply going to init it. Let's say def init, and then we're simply going to pass in here cell the d in, the d out, okay, the dropout, the number of heads, okay, and the QKB bias is equal to is equal to false. Okay, fine. So okay, we also miss one thing, that is nothing but our context length. So we can pass it to here. Let's say context length. Fine. So context length is essentially the length of the actually the inputs, and then you can say the super constructor, and you can essentially using here this init. Okay, so okay, super dot init. That's it. Fine. Now we simply going to initialize here all of the important the variables that you can initialize it in ourself. So you can say that self dot the self d out is equal to the d out. But here is one catch. If I go on the middle that you can see, So we see that the number of hat dimension is essentially the d out divided by number of hats. It's mean our number should be the divisibles with a d out by number of hats. If it is not divisible, so we cannot go further. We cannot go further. So what you can do, we basically using here one assertion error. Okay, we can give one assertion error if the divisible is not happens. So if the divisible is not happen, we cannot essentially get in here this hat dimension, right? So we can simply going to give it to here one the assertion error. So before that, let's say assert, and then we're simply going to divide them d out and the modulus of the number of hats. So let's say number of hats is equal to 0. It's when if it is divisible by number of hats, we move further, right? So you can say that the d out, okay, d out, you can say the d out must be divisible, okay, divisible by the number of hats. Fine, cool. So if it is not divisible, so it's obviously give one assertion errors. Now initialize here the d out. Now you simply can initialize here the number of heads. Let's say self dot number of heads is equal to number of heads which is coming from the parameters. Okay. And then you have the self dot head dimensions. So head dimensions. So you see in the middle that you can see the head dimension is essentially the d out. Say d out divided by the number of heads itself. Okay. So we can say that the d out and divided by number of heads. So in GPT, it's actually using here the same size of d in and the d out. But in previous video, you see that we actually using here the d in as a 3 and d out as a 2. But in this case, we're just going to using here the GPT ones. I mean the same size of the d in and same size of the d out, because it's necessary. When you go to the further, then you know that when you combine the unroll functions, that you know that why should you actually using the same size. Okay. Now, after that, what I can do is simply going to initialize here the self dot the W query. So we can using this one. So this is nothing but a step for initializing here the trainable weights. So you have the 3 trainable weights: weight, I mean the key, query, and the values. Okay. So what you basically do is just going to multiply them with input X with the WQ that you can see. We discussed everything in previous, right? You can see, okay, input into WQ, input into WK, and input into WB. So we just do it randomly, but you are not going to do it randomly because you're going to using here the linear layer. So that you already do this, we can copy it from here. We can directly copy it from here. So we are not going to do it. The self.w query, the and not here because it have the best weight matrix, weight initialized parameters. So we can using here this d in, the d out, and bias is qpv bias. So this is the initialization part of the trainable words. Okay. Then after that we have our the output projections. So let's say output projects. So projection is nothing but our nn dot linear, and if it's nothing but the d out by d out, because this is the output layer itself. So the main goal of the multi-hat attention is to creating here a context vectors. Okay, that's our main scenario. Okay, so we can using here this output projections before the context layer calculations. So let's say self dot, you can say that the dropout. So let's say dropout is equal to nn dot dropout. So it should be the capital. Okay, नहीं तो भाई बहुत error देगा. So you can passing here the dropout itself, which is coming from the parameter that you can see. And then we're simply going to using here the register buffer, because you need to also register the buffer for the mux. Okay, let's say register buffer. So our main thing is coming how you actually implementing here the foreign methods, because all the mathematics is inside these foreign methods. So we can copy it from here because I'm so lazy. So you can copy it. This draws a trio and we can essentially copy this out. So what you can do, you can test it out. So traws dot, okay, we are not going to using the trio. We are going to, traws trio and traws once and context length and the context length and the diagonal as a once. Okay, fine. So this is nothing but all of the initializations. Now we are going to creating here our forward method. So let's say def forward. So taking cell and the access input. Cool. Fine. So first what I can do is simply going to taking the shape, and it give me three things. One is the batch size. Okay, obviously it give me some error. Batch size, the number of tokens, let's say number of tokens, and the in. Okay, now let's go on the board and let's discuss about it. So this is a step number one, we can say that. So this is a step number one. Here we basically start with inputs. So you have the x dot shape. So x dot shape is containing here three things. One is a batch size, another one is the number of token, and another one is d in. So let's say our batch size is, let's say, 1, and our number of tokens, let's say 3, and the d in, let's say 6. Okay, what it actually means, let's say we have a word called go and slip. So it's mean for each of the word, it will creating here the 6-dimensional vectors. It will creating in the 6-dimensional vectors. Same thing for and, same thing for slip. And 3 is nothing but number of token. How many token you are using? See, it have the word called go and slip, but if you are using the byte pair encoding, the token might be the greater than 3. It may be happen. Essentially, it may happen. Just we're taking here one the quantum things. Okay, so you can see not quantum, classical things, right? Okay, if you take it the quantum, so it should be the qubits. Okay, it's not essentially the range of 0 and 1. It should be range between 0 to not 1 if you're using the quantums. Okay, you're not going to discussing the quantum physics here. Okay, so number of tokens and the d in. Let's say we have 1 2 3 4 5 6. Let's say 7 8 9 and the 10 11 and 12. Let's say 13 14 15 16 17 and 18. So this is nothing but, let's say this is one vectors, this is one another vectors, this is another vectors. So let's assume that this vector is corresponding to word called go, and this vector is corresponding to the word called the and this vector is corresponding to the word called slip. So each of this vector, it's nothing but one 6-dimensional vector, right? It's a 6-dimensional vectors. So it's nothing but the dimensional vector space for the word slip. And you can see it's nothing but one batch, that you can see one batch, and it have the 3 row, because you can say the 3 row, this one, this one, this one. Okay, it has the 3 row. That's mean 3 number of tokens. So this is the first step, just starting with the inputs. Now after that, we need to deciding here the d out and the number of head. The step number 2 is nothing but the decide. You can say that decide the d out and the number of heads. So number of heads, how many heads it have. Okay, so as we're taking here the d out as a 6, and number of heads is basically 2. Okay, now each head of the dimension of the head dimension is, because if I see in the book this graph, you can see we splitting the queries q into q1 and q2 based on the head dimensions. So we're taking it the height dimension from here. In the GPT, it actually using here the head dimension is the number of head is equal to 96. So in here we're just using here the number of head as a 2. Okay, just for the explanation purpose. And the head dimension is obviously, the head dimension is equal to the d out by the number of heads, right? You already implemented that, you can see you already implemented before that. You can see the number of heads equal to the d out and the number of heads. Okay, and the step number 3, is basically the initializing the train evaluate. So it's a initializing, or you can say initialize train able weight. I mean, I'm talking about the key query and the value matrix, which is changeable when you training your models. Okay. So in the case of this key query and value, the dimension is basically 6 cross 6. The dimension is basically 6 cross 6. Here, this 6 is nothing but our D in, and this 6 is nothing but our D out. For the case of the key query and value, and you already initialize this, that you can see a W query, W key, W value. So this is nothing but our initializations. Now we need to calculate. Now we need to calculate here in the step number 4. In step number 4, so we need to calculate the keys, the queries, and the values. Sorry for my bad handwriting. So how can we basically calculating here the keys, query, and the values? We essentially multiply them with the inputs into the WK inputs into the WQ. We already actually discussed about that. What is the input matrix? What is the WK and what is the WQ and what is the WB and what are the use of them? Okay. Now and this case the dimension is basically the 1 cross 3 cross 6. So here b the batch size, 3 is the number of token, and 6 is nothing but our d out. It's our d out here. I mean, see, because we see that the d in and the d out is essentially the same. So when we calculate them this in step number 4, we can say that this is nothing but our d out. This is our C, the D out. But here is also one problem. See, if I see that B, the number of token, and then we have the D out. Okay. But here is one thing is missing. That is called we don't have the dimensions for the hat yet. We don't have any dimension for the hat yet. So you need to also implement them. We need to also implement them. So you know that D out is nothing but called hat dimensions into the number of hats. Okay, कैसा है देखो थोड़ा आगे जाता है उसको. So we see that in our step number 1, the head dimension is equal to D out. So if I cross them diagonally, so D out is equal to number of heads cross, the head dimensions cross the number of heads. So you can replace this D out with the head dimensions and the number of heads. So the shape would be look like that. The number of the tokens. So in this case of the in this place of the D out, we can say that this is the head dimensions and this is the number of heads, because we don't have any dimension for the head, because we need to also calculating here how many heads it have, and using this head we simply going to calculating here the context vector. That's our main thing. That's what is called the multi-head attention, right? But in here you see that in our shape we don't have any the dimensions for the head, so we can calculate it from here. Now let's try to first implementing it here, the calculating in the key, query, and the values. So what you can do, let's go on the code and let's see. So we can see that the keys is equal to the self dot w key, and you can directly passing here the x, because this is a linear layer itself, and we can directly do the matrix multiplication on here. We don't need to do that. We usually do that. So for the queries, so you can say that the self dot the w query, so w query, and you can pass in here the x, and here we can say that values is equal to self dot w values, and you can pass in here the x. Now the input shape is batch size, the number of tokens, and the d out, because we're using here the key, query, and values that you can see, key, queries, and values. Okay. Now the shape is look like the batch size, the number of tokens, and the d out. Now in in the next step, what I can do in the step number 5, I hope so. So in step number 5, we basically unroll. Okay, step number 5, we basically unroll the last dimension. See, we unroll the last dimension of the keys, queries, and the values. Now, why? Because we know that the head dimension is equal to the d out divided by number of heads. So our d out is 6 and number of head equal to 2. So our head dimension is equal to 3. So why you need to unroll them? Because we just going to replacing here this d out to the number of head dimensions and the number of heads itself. Okay, that's why you need to unroll it. You need to unroll it. Okay, I mean we're changing here the 3 dimensions, the vector space to the 4-dimension vector space. Okay, 3-dimension vector space to 4-dimension vector space. So now this batch size and the number of token and the d out is changes into the batch size, the number of tokens, and the number of heads, let's say number of heads, and the head dimension. So you know that the dimension is batch size is 1, number of token is equal to 3, and d out is equal to 6 because it's the equivalent to the d in itself. Now here batch size is 1, the number of token is equal to 3, the number of heads is basically the 2, and the head dimension is 3. You got it here, it's a 3. So after that, the shape is changed like that. The batch size, the number of tokens, the number of heads, and the head dimensions. Now let's implement it in the codes. Okay. So here what I can do is simply going to say that the keys is equal to keys.view. You can using here the function called view for changing the dimensions. We can pass in here the b, the number of tokens, and then we can using here self dot number of heads. Okay, heads, and self dot the head dimension, because it's on here. It's on here. You can see number of heads and the head dimensions. Now I need to also do it for the values as well. So let's say values. So we can copy it. We can copy it. So let's say the values. Okay. Dot view dot b number of tokens, self dot number of heads, and the head dimensions. Let's do it for the queries as well. Okay, let's say QU queries, and you can say that this is for the queries. Okay, queries.view and b number of tokens, the self dot number of heads, and the head dimensions. Cool. Now after that, what I can do, I mean our step number 6. So let's go on here. So yep, fine. Now in step number 6, we basically creating here a group matrix by the number of heads. See, it's quite important, right? So now we have the matrix called b, the number of tokens, the number of heads, and the head dimensions. शायद बाहर बारिश हो रहा है. So this is nothing but our dimensions. Now we need to changing this dimension into b comma number of heads, the number of token, and the head dimensions, and our head dimensions. Now why? Now why? So let's go on here the presentation slide. This slide is basically for the transformer architectures. See, in here we have our inputs. If I go on the full screen mode, I mean here. So you can see you have the uh, we have this one. Okay, we can see Q matrix, we have the K matrix, we have the B matrix, and we multiply with the QW, I mean WQ, WK, WB, and then you can see you have the multiple number of heads, 1, 2, 3, 4, and after that we join them and we got in here a multi-head attentions. If you see this is nothing but attentions of the QWQ, KWK, BWB. It's mean that first we have one dimensions for the number of heads so that we can join them. So this is nothing but the number of heads itself. This is our number of head itself. Now if I go on the code, just to white, if I go on the code, so we basically multiply with this one. We multiply with this one. If I have a dimension called it's 1 comma 2 comma 3, and it's a 3 comma 4 comma 5, and let's 6 comma 7 comma 8. So this is nothing but our hat 1. Let's say this is our hat 1, because we just going to multiply with, I mean we multiply with the number of hats. Okay, we have the hat number 1, we have the hat number 2, we have the hat number 3, right? So we have those matrix, and that's why you need to transpose this matrix. I mean we're just changing the position of that. See, we're just changing this position. The number of head is coming on here, the number of head is coming on here, and this number of token is just gone here. That's the points. That's called group matrix by number of heads. It's mean the base size and the number of heads is basically one group, and this number of token and the head dimension is also one group. Okay, that's it. थोड़ा बहुत बारिश हो रही है, मुझे फैन को बंद करना पड़ेगा, फूट जाएगा भाई. Okay, fine. Now, in step number 7, what I can do basically, we simply going to find the attention score, but let's implement this out. Okay, शायद बाहर बहुत बारिश हो रहा है मुझे लगता है actually. Okay, so let's say keys is equal to the keys dot transpose. You can say that 1 comma 2. Now why this 1 comma 2 basically? See, so you transpose the matrix. If I see that this is the index number, the 0, index number 1, and index number 2, and index number 3 basically. So because we are using here the Python programming language, so obviously start from 0, right? So we're just going to transpose this matrix and this matrix. That's why transpose 1 comma 2. Transpose 1 comma 2, because it's just replacing the dimensions, so that we can grouping the matrix, and we can multiply each of them. Okay, समझ आया ना आपको? अब चलते हैं, इसको इम्प्लीमेंट कर लेते हैं भाई. बहुत बारिश हो रहा है, मुझे रिकॉर्डिंग स्टॉप करना है, मुझे थोड़ा जल्दी. So let's say values dot transpose, and let's say 1 comma 2, and same thing for the queries. भाई बहुत गर्मी हो रहा है. Values, okay, sorry, queries, queries, and we can say that the transpose of the 1 comma 2. Okay, fine. Now after that we need to calculating here the attention scores. Okay, now let's say step number 7. Step number 7. So step number 7, we need to finding here to find the attentions score. Okay, fine. So how you can basically find the attention score? So if I see that our matrix is 1 comma 2 comma 3 comma 3. So here our 1 is our base size, and now 2 is our number of heads because it changed the dimensions, and 2 is our number of head, you can say, and h, and this b is number of token, and t, and this is our head dimensions. It's our head the dimensions. Now what we can do, we now simply going to do one thing. we just go to one thing because this is really important to calculating while you're calculating the attention score. So we need to just changing here these dimensions called batch size into the number of heads into the number of token into the head dimension into from from this to batch size the number of heads, the head dimension, see, head dimensions and the number of tokens. See, now we're converting here this batch size into number of heads, into number of tokens, and head dimensions into the batch size, the number of heads, the head dimensions, and the number of tokens. Now, if I taking here this group, it's taking here the green pen. If I taking here this group and this group and this group and this group, and just write it here, let's say number of token, and we have the head dimensions, this one, and then let's say the head dimension and the number of token. So those are two matrices. If I multiply them, so our matrix should be look like that: the number of token into the number of tokens. So our final matrix is look like that. Let's say we have the number of token called 6 and head dimension, let's 6, sorry, 2. And now head dimension is 2 and number of token is equal to 2. If I multiply these two matrices, so our dimension should be look like that, because the middle of this value is gone. This value is gone, and we got it in the matrix size of 6 cross 6. Same thing actually happening on here. If you have the number of tokens, the head dimensions, and head dimension into number of tokens, so we essentially got in the number of token and the number of token. Now, why it's basically needed? Why it's basically needed? Because so we know that our step number 7 is basically finding the attention score. Now, finding the attention score from where? Finding the attention score from the what? Or from the context vector. So find words from the actually the you can say that the tokens, sorry, tokens, I mean how many tokens we have. Let's say we have the scientist call go and sleep. Okay, go and sleep, let's say sleep. So what we basically do, we're creating here a matrix like that. Okay, and each of the matrix we have the go and sleep, and then we calculating the attention scores. So those are basically number of token, number of token, number of token, number of tokens. So you need to multiply them, and our dimension is look like that: number of tokens into number of tokens, number of tokens and number of tokens. And after that, we basically calculating here the attentions weight as well as, and then you can also calculate the context vector. That's why you need to do these things. So it's actually happening, but uh, okay, let's implement it first, then we talk about that attention weights. So now what I can do, we are simply going to actually implementing this out. So what I can do, you can say that attention scores, so you can say that attention scores, and then you can say that the queries and dot queries at the rate of the keys dot transpose of the 2 comma 3. Now you see that why this 2 comma 3 basically, because this is the index number of 3 and 4. So let's say 0 1 the 2 and the 3. So just changing here these dimensions 2 comma 3. Now the dimensions look like that. The head dimension is coming on here. So after that, we basically got in here our attention scores. Okay, we basically getting here attention score, right? So that's when it also transpose it after actually the transport with the query and the key. Now why we need to actually transport here transpose here the keys matrix. If I see the previous one, you can see if I multiply them, if I multiply the this matrix and this key matrix, we need to also interchange these ones. Interchange, I mean to transpose the matrix. If I have a matrix called, let's say, 6 cross 3 and as well as 6 cross 3, so you cannot multiply them. So obviously one of the matrix should be the transpose. So if it is nothing but the, okay, if it is, let's say, 3 cross 3, so another matrix should be the 3 cross 6, then we can multiply them, okay, otherwise not. So that's why, because the query matrix and the key matrix are essentially the same dimensions, so you need to also transpose one of the matrix, so that you can also calculating here the attention score. I mean, you can creating here this kind of the matrices actually. So now what I can do is simply going to go on here, and after that we basically transpose here 2 and 3, because you need to change the dimensions of the number of hats and the token itself, okay. So now we can simply continue using the max ball. So max ball is nothing but for the causal attentions. If I see that in the slide little bit, so this is the slide for the multi-hat attention, I mean max multi-hat attention, or you can say the causal attentions. So here this diagonal part of this value is the converted into the minus infinity, okay. Our goal is to make the model casual, that you can see it's mean the output at certain positions can only dependent on the words on the previous positions. So this model must not be able to see the future words. So then you can basically calculating here the loss, that how our model is trained and how it able to predicting here, I mean the next word, okay. So we simply going to creating here a max ball. We already discussed everything in our causal attention class, that you can see that here you go, you can see the max field, okay. So we're creating here a max ball. Let's create that. So you can say that the self, okay, self dot the max dot bool, and then we're taking for number of tokens, I mean how many tokens it have, and the last of that, because we're creating the max, that how many tokens we have, and based on that token we basically creating the max. If I see in the slide, so you have the word called I love you in every universe. So it basically have the 6 word. It's when the context length is basically 6. So for the 6 word, I mean 6 cross 6 matrix, we essentially creating here, considering that as the number of tokens. Okay. So just taking from the 0 to the end of the number of tokens, and you're creating here the max of that. And after that, what I can do is simply going to creating here, I mean, we calculating the attention score dot maxed field. Let's say maxed fill, and then you can pass in here the maxed bool, and then here you go, we're simply going to give it to here np dot infinite, okay. I mean we're just getting here a max, I mean the diagonal value is basically the essentially actually the replace with the minus infinity that you can see on here. Now our the step number 8 is basically our the calculating here or finding the attention weights. So it's our step number 8. So let's step number 8. So find the attention weight. Okay. So it's basically the maxed one. I mean the maxed, the attention, I mean the causal attentions. So you're already implementing here the max one that you can see. So what I can do, we're simply going to calculating here this attention weight from here. So let's say attention weights is equal to torch dot softmax. So attention weight is basically normalizing that in the summation of 0 to 1s. Okay, that's the thing. Okay, so let's say attention scores, and then we can divide them keys of -1, so that it taking hit all of the columns, I mean the head dimensions based on that, how many dimensions it have, and then you can simply going to multiply with 0.5, I mean root over decay, that you already discussed about that, how the variance actually increases. And so dimension of the -1 is so that it can taking here all of the columns. Okay, so softmax attention score by keys dot shape, okay, not keys or shape, it should be the shape, keys dot shape of -1 and this into 0.5, and dimension is basically minus 1. Okay, after that we're simply going to using here the attention weights into the dropout. So let's say self dot dropout of the attention weight itself. Okay, let's say attention weights. Okay, and after that we are basically calculating here the context vectors. Okay, the main important part is here. So we can say that step number 9. So let's say that is step number 9. So we are going to calculating here the context vectors. So how we basically calculate the attention vector? We just multiply them with the attention weight with the values matrix. Then we got in the context vectors. Now our dimension is basically the B and the number of heads, the number of tokens, and the number of tokens. Okay, so that's our dimensions, right? So you can see that's our dimensions. After that you can see it's converted this head dimensions, number of tokens, I mean number B, number of heads. Now it's after the multiplication is number of token and number of token is converted. So now we need to making this matrix like that. It should be converted into base, number of token, and the D in, like that. We need to convert it. I mean the previous shape, I mean X, our input, it's previous like that. Okay, now how can we basically converting here this 4-dimensional matrix into 3-dimensional matrix, and how we can basically flatten them? So if I see this one, if I just am going to replacing here is the number of heads and the number of token, I mean, sorry, okay, it should be the, okay, not like that actually. So this dimension is for the attention weight. Sorry, okay, sorry, my bad actually. This dimension is for the attention weight. But if I see the dimension of the vectors, I mean values, it not changed yet. If I see in the code, see, we are not applying any things in our value matrix. We just apply it for the query and the keys. We not apply it for the value matrix. So if I see the dimension of the value matrix, so it look like that. The base size, the number of heads, okay, sorry, the number of heads, and the number of tokens, and the head dimensions. Okay, so this is basically dimension of the values. So if I matrix multiply it with the number of tokens and the head dimensions, so we can getting here a dimension the same exactly like that. Okay, this dimension is changed if it exactly like that, so we can interchange it here. So our the matrix dimension is basically base size, the number of heads, the number of tokens, and the head dimensions. Now if I interchange this one, let's say if I interchange, let's say base size and the number of token and the number of heads to the head dimensions, and we can directly writing here the D in. We can directly writing here the D in. Now why D in? Because if I see this one, we just writing here D out. In this state, we just writing here this D out. I mean D out equal to head dimension into the number of heads. But in GPT, our dimensions of the D out and the D in is same. D out is equal to the D in. Now in the case of the D out, we can directly say the D in. That's our input. Okay. So after the conversions, we can getting here the matrix of the D in. Okay. So we're just having these two matrix, this B, the number of heads, and number of tokens and number of tokens. If I multiply them, so if I multiply them, So it look like that. So this is the two dimensions. I mean this one and this one, and this one and this one. If I separately write in that, so let's say we have the number of token and the number of token. I mean, it's just grouping them, and then you have the other dimension called number of token and the head dimensions. So this is the last dimensions, last two dimensions of the attentions weight, and these are the last two dimensions of the value matrix. So if you multiply them, let's say multiply them, so this is basically cross. So our dimension is look like that, the number of token and the head dimensions. And then you can say that this is the base size, and this is nothing but, okay, the number of heads. Okay, number of heads, we can say that from here. So the number of token is gone actually. This number of token, yep, this number of token, this number of token, and this number of token is gone. Then you have the number of tokens and the head dimensions. Okay, सॉरी माय बैड, एक्चुअली इलेक्ट्रिसिटी चला गया था तो मैं फिर से चला गया ऊपर रिकॉर्डिंग करने के लिए. Okay, now what I can do is simply implementing here this thing that we discuss on here. So we're just going to changing the dimensions of the base size, the number of heads, the number of tokens, and the head dimensions. So what I can do, you basically go on here. So let's say that uh, because we are going to actually calculating the context vector, that's our step number 9. So let's say context vector, let's say context vector is equal to the attention weights. That's our attention weight, and you can say that the values matrix. Okay, and after that you simply going to transpose it. So let's say transpose of the 1 comma 2 y. So let's say y 1 comma 2. If I go on here, you can see that this our attention weight and this our value matrix. So after that we got in here the base. I mean, you can see the base size, the number of tokens, the number of head, and the head dimensions. Okay, so what we can do first, now is simply going to actually the replacing here, I mean uh, transpose this base size, the base size and the number of tokens. Okay, we're just replacing here this position of that. Okay, because our dimension is look like that. Our dimension is basically the base size, the number of heads, and the number of token and the head dimensions. I mean, after the multiplications. So we're just changing here these dimensions. Okay, this number of token is go in the position number 1, and this number of head is coming in the position number of the 2. Okay, that's our main goal. Okay, so you can see after that. So let's go on here and try to do the transpose. So you can see transpose 1 comma 2. So it is basically replacing here this two position of the number of heads and the number of tokens. Okay, fine. Now after that, what I can do is simply going to contiguous it in the shape of uh, the base size, the number of token, and the d in that you can see. We're just going to convert it. Okay, so how we can do that, we can basically using here this context vector, and then you can simply going to using here this context vector dot contiguous. Okay, let's say contiguous contiguous, and then you can using here the view, and then we pass here our base size, the number of token, and the self dot d out. Okay, so d out is basically our d in itself, because the size is exactly the same thing. And then now we can simply going to say that the context vector is equal to self dot the output projections, and you passing here the context vector itself. Okay, then you can return here, so you can return here the context vectors. Okay, So this is our multi-hat attention class. Now let's try to testing this out. So what we can do basically, we can copy this out and we can paste it to here. Instead of the multi-hat attention wrapper, we can using here this multi-hat attentions. Okay, so you're passing here the d in, d out, context length, and dropout 0.0, and number of hats is basically the one two itself. Okay, now here we give it to here the d out. Okay, we're just changing this one. So taking the base size, so let's say base size comma the context length and the d in from the base dot shape. Okay, I mean from the full shape, then you have the d out is equal to 2 itself. I mean the same size of d in and the d out. We initialize everything on before that you can see d in and d out. Just changing this d outs. So now if I running this out, we got some error maybe. So attention score is not defined. So it should be the attention scores. Okay, it should be the attention score. I hope so. So attention scores. So attention scores. So here we go. So now you can see that we have the tensors. That's our tensors, and our context vector shape is 2 comma 6 comma 2. So 2 is basically our base size, and 6 is nothing but our number of tokens, and our 2 is the d in. Okay, you can say d out. I mean d out or d ins. So you can see the same size of that. So that's our main thing to implementing the multi-hat attentions. Okay, with the weight split. So that's it for today now, and I hope you enjoy this video. So the next couple of videos, we try to implementing here a GPT model from scratch to generating the text. That's our next topics. If I go on the book, you can see implementing the GPT model from scratch to generating the text, and we coding here a large language model architectures. Okay, finally in our tutorial number 11. So thank you and bye bye.